Okay, we've looked at sediments, and now I want to look at layers and strata. I mean, sediments are packaged as a layer, and a layer is a depositional unit that may contain a mixture of different sorts of sediments, and probably almost always does contain a mixture of different sorts of sediments. A layer is a unit, but it's not necessarily an event. A layer can be something that builds up over several thousand years because the inputs have stayed stable. The processes that have created that layer have continued to operate over a long period of time. Or a layer can be simply an event where a dike has broken and a plug of sediment has been laid down very rapidly. How do we go about looking at a layer? Well, first of all, let's think about it in terms of its components, in terms of the different sorts of sediments that it contains. Let's think of a layer in terms of its structure, its horizontal and its vertical structure. And let's think of a layer in terms of its rate of accumulation. So let's take each of those in turn. First of all, the components. Well, I've made the point, it's not usually just a single type of sediment, but a mixture of different sorts of sediments. And you need to identify the different elements in terms of the overall sediment flux. You might have material that's input from the bedrock. You might have externally derived sediments, which might be fluvial or aeolian. And you'll have anthropogenic material from people living on the site and bringing stuff in and lighting fires. Now, characteristically, a lot of Australian rock shelters, particularly arid zone rock shelters, reflect a shifting balance between external sediments, usually aeolian sand, and weathering of the bedrock. And so some layers which are dominated by weathering of the bedrock are going to have a lot of relatively clean sand and rocks and rubble, and layers that are dominated by aeolian inputs are going to have red sand and maybe any clay that comes in bound to the sand and so forth. When I analyse the particle size of sediments at my Central Australian sites, I can often see some distinctive size modes in terms of peaks. We might get one for gravel, which represents material from the rock shelter wall, and if you look at that gravel you can see it's patinated. You can see it's been on the wall and it's pinged off. We might get a peak at the fine sand, which is typically 100 to 150 micron sand, which is absolutely characteristic of windblown sand. That's what all the dunes are made of in the Simpson Deserts. And you might also find a smaller peak in the clay, which in the case of Puritjarra is the stuff that came in around the sand. So somewhere along the line you've got to try and disentangle what the different inputs are. A very extreme case, of course, in terms of a riverbank and swamp deposit is one of the megafauna sites, and I think it might be Redstone Creek, it might be one of the other ones, where Tim Flannery showed that when he went back to reinvestigate the megafauna site, all the megafaunal bone was in these big clods of earth that had been eroded out of a bone bed and moved, perhaps not moved very far, down the fluvial system. And so if you cut the section, you found you had clods of earth with bone surrounded by finer sediment. So you've got to have a look at what's in your sediment and how it's packaged. Structure. Well, a layer also has both a spatial and a vertical component. The sediments are configured in space. You might have variation across the site. The sediments against the wall might be quite different from those in the middle of the site, might be quite different from those in the drip line and outside the shelter, but it might also be all one layer, and it's useful to introduce the concept of facies. Facies or facies is the sort of local variability you get in an assemblage of material depending on its position. For instance, a classic case of facies is along an alluvial fan, where you get coarse material here and you get finer material there. Now, in an archaeological site, you might find that external inputs, aeolian material blowing into the site, more strongly influences the deposits towards the front of the shelter, and when you get towards the rear of the shelter, you've got more material derived from weathering of the rock shelter wall. But it might all be the one layer. So layers may vary in their characteristics across the length. Layers of course may vary vertically as well. I mean, classically we've talked about how fluvial deposits grade, but small differences in the balance between the sedimentary input, between external sediments and internal sediments, or between whether you're getting material blown in from the crest of a dune or the interdune corridors or whatever, may gradually change the character of a layer vertically through its depth without there actually being any major layer boundary. And of course, this raises the whole issue of how you correlate your stratigraphy between different trenches. You really need to have an eye to the concept of facies. Otherwise you're suddenly going to find that you've got a stratigraphic sequence at the rear of a rock shoulder that really looks quite different from that at the front of the rock shoulder or at the entrance to a rock shoulder. It might all be just a one layer with variability across it. Of course you need to have an eye to how that layer has been draped over a site. Water-laying deposits are generally going to be horizontal, by definition. But other sorts of sediments, windblown sediments, may slope across a site. They may build up against obstacles. Sand may build up against a rock ledge. They may be horizontally bedded, as we've said with fluvial deposits. They may be localised in depressions. You may have sand or organic material that accumulates in a depression in the floor, or you might have ponding where water flows in and forms a little deposit in a depression. You might have a mantle or drape. You might have in situ decay of rocks. If you get a big patch of white sand in the middle of your section, what's it doing? Is it a burrow that's filled in with sediment, or is it just a big boulder that is decayed in situ? You might get a mound or a bench of sediment. If you do, what's going on? Has sediment been cut away? Often in stratigraphic drawings, people draw a line around an area of mottling or discoloration, and they're drawing it with a vertical face. What's happening? Sediments aren't laid down with vertical faces, they're laid down in terms of lenses and beds. If you've got a vertical face, it implies something has been cut away. You need to have an eye for that sort of structure. You also need to have an eye towards the processes that lead to evolution of a rock shoulder. There's a classic process called rock shoulder retreat. Rock shoulders form by cavernous weathering, an area often at the base of an escarpment where a bit of moisture enhances chemical and mechanical weathering. And that cavity gradually retreats back and upwards into the rock. The overhang it creates may or may not be structurally stable, and characteristically the lip of the overhang collapses over time, so the rock shoulder retreats back. This is Fromm's Landing, one of the rock shoulders on the Lower Murray, excavated by John Mulvaney. Twydale, who was a geomorphologist with the party, pointed out there was an interesting relationship between how the sediment accumulated in a deposit and erosion of the rock shoulder wall, so that when you had a zone of occupation, you had a vertical wall because you had rapidly accumulating deposit which protected the rock shoulder wall, and when you had a zone when you had very little occupation, you had the opportunity for the rock shoulder wall to erode laterally. So you got a series of steps. So there's an interaction here between the extent of cavernous weathering and the way occupation deposit protects the rear wall of the shelter from weathering. If you're trying to decide where to dig to find the older deposits at your site, you need to understand what rock shoulder retreat is doing. If you look at any of those pictures of excavations at the classic French Paleolithic Dordogne sites, they're not actually digging in rock shoulders, they're digging on the slope outside the rock shoulders, which used to be part of the rock shoulder but is now part of the Taylor's slope. They understand they're digging within what was once a rock shoulder, but the edge has collapsed periodically. An example of what you can do here is given at Puritjarra. We explicitly dug a pit under the edge, the leading edge of the overhang. We wanted to see if we'd had any rock shoulder retreat over time. And what we found was a column of rocks in exactly the same position right through our stratigraphic sequence. What this was showing was little rocks had been falling off the edge of the overhang for 10,000 years and landing more or less in the same position. There'd been no real retreat of that overhang. That rock shoulder was phenomenally stable over time. When you're looking at the weathering of a rock shoulder, also have a look at what's happening inside. You may have a domed roof, or you may have rock ledges against the back wall that are collapsing. A domed roof might be an area where you get a lot of spalling and rockfall beneath. You might have a cone of rockfall beneath a domed roof. Have a look where the structural controls are, where the joint lines are. There's something called unloading. When you take the pressure off a rock formation, things start to ping off. The classic case is Uluru, which is Arco sandstone, but the layers are pinging off like layers of onion skin as the pressure has been taken off. You can get things like this happening inside a rock shoulder as well. So rock shoulders can change their form over time. The whole configuration of a rock shoulder can change, and you need to understand what you're looking at and which part of a site you're looking at. Okay, this is a global diagram from Puritjarra rock shoulder. It shows the changing proportion of coarse rocks and gravel, and the fine sediments in terms of sand, silt and clay, and also the proportion of grass in the phytolith column. And what it shows is, on a global diagram like this, you can see a whole series of related changes between layers 1 and 2 at about 8,000 years ago. The size of the rocks change. You get a lot more fine gravel, you get a lot less large rockfall, you get a change to a much more sandy deposit, and a great increase in the proportion of grass. So you've got a whole range of changes here that relate to the changing local environment of the rock shoulder. But it's the ability to compare across these different materials that makes these diagrams useful. So you're also looking at the lateral relations of a layer or a series of a layer across a site. You're looking at the bedding within a layer. Rockfall I think represents an opportunity. One of the few things you can see in a stratigraphic section, if you can't see anything else, is you can see the rockfall and the rocks. Every rock that has fallen on a surface. It may be just one of these very temporary ephemeral surfaces, but it's a moment in time. Every surface then gives you some clue as to the bedding and slope of that deposit. So have a look at how your rocks lie. They're the grain of the deposit. They're an opportunity to get some sense of its structure and an indication of a surface. And of course, when you lift a rock, you're lifting it off a surface that has a fair amount of integrity. What's on that surface is a charcoal underneath the rock, etc., that you can use. And then move towards the front of the rock shoulder. Rock shoulders may be at ground level, or they may be raised. If they're raised above ground level, above the surrounding countryside, they'll have a talus slope. Have a look at that. Is that just a collapsed lip of the rock shoulder? Is there more to it? How do the sediments within a rock shoulder relate to those outside the rock shoulder? In many cases we find that even the occupation extends outside the rock shoulder. In fact, many rock shoulder sites are just one end of a wider occupation site that's essentially an open site. Have a look at how those deposits enter the rock shoulder, how they feather in or lens into the rock shoulder. You need to pay some sort of relationship, some sort of attention to the relationship between interior and exterior sediments and deposits. So we've looked at the components, we've looked at the structure, and let's look at the rate of deposition. One of the key things that's important is how fast is that layer built up. It makes a difference to how you interpret your archaeological remains, which we'll talk about in a minute. One of the first questions to ask is what's initiating sedimentation? What might be triggering build-up of sediment? A classic thing is where you get rockfall across the mouth of a rock shoulder. A big boulder falls, and all of a sudden you've got something that will retain sediment, so sediment can start to build up. You might get some other trigger, which means that sediment builds up very rapidly. Or it might be something happening in the wider landscape, whereby you've got a period of aridity, vegetation is dying away, and all of a sudden you've got exposed land surfaces that are eroding. and that material is flowing or blowing into your site in some way. But have a look. What are the possibilities for factors that are triggering sedimentation? And even within a shelter, if you're starting to get a lot of material that derives from the rock shelter walls, what's likely to be causing it? Changes in moisture, temperature, salts. Is it because animals and people are changing the microenvironment within the shelter? Is it because external climate is changing and that's changing the moisture regime? Is it a gradual process of weathering, or is it some sort of structural collapse? I mean, you may have a rockfall layer. That rockfall layer might be a gradual accumulation of rockfall over several thousand years, or it might be a single event in one catastrophic fall. Have a look. Is there any internal structure within that rockfall that indicates it's a series of smaller rockfalls? I want to move as we look at the rate of deposition to a really key concept: net sediment budget. We know that fine sediments are removed from sites. Most archaeologists really don't quite grasp the idea that sediments are routinely removed from their sites. We wouldn't have rock shelters if sediments weren't removed. You know, you go to a rock shelter, it might have a ceiling height of 2 meters, it might be 20 meters across and 10 meters deep. There's quite a few tons of sediment that have been removed to create that void. If it hadn't been removed, we wouldn't have a rock shelter, we'd just have a pile of sand. So there are processes that evacuate the sediments, and there are processes that introduce sediments. So we've always got a balance between removal and accumulation. The deposits built up if the inputs exceed the removals, and vice versa. Ingrid Ward developed a really nice model for sediment accumulation in northern Australian rock shelters, and you can imagine it as a bit of a clock. When the hand is horizontal, sediment removal equals sediment accumulation. You've got zero net sediment budget. So you've actually got a surface, you've got a paleo surface, and that means that all your activities, all your occupation is happening on the surface, and you're going to get a palimpsest of material over time. However long that surface survives, thousands of years, hundreds of years, or whether it's a more ephemeral surface. When the hand is pointing vertical, where you've got a very high positive sediment budget, so you're getting rapid accumulation of sediment, you'll find that discrete occupation events might be quite nicely separated stratigraphically. So you can get a band of occupation, then a band of sterile sediment, and a band of occupation. It's really an ideal situation because you can get high level resolution in your archaeological record. If the hand is starting to point closer to horizontal, sediment accumulation is not so rapid, you don't get as good a separation of your occupations. You tend to get overlays. If the hand is pointing straight down on this clock, where we've got extremely negative sediment budget, your sediment's being removed from the site. In fact, sediment that might have accumulated over a period of time is just gradually wiped away, and what it will leave behind, depending on what processes are removing the sediment, might be a lag of artefacts. For instance, we see this at Cuddie Springs, where there's a stone layer which is almost entirely made up of stone artefacts, which represents all the coarse material that's been left behind as wind erosion has removed everything else. At some stage at Cuddie Springs, sediment's built right up and then were cut right back, just leaving this stone band. Similarly, in dune sequences, you often find where you've got a blowout and you've got lots of stone artefacts. Those stone artefacts have been let down as the fines have been removed. They may then be reburied and recycled and let down again. You may have coarse material, stone artefacts, or it might be tooth enamel of megafauna bone that's moving through a Aeolian sequence. And then somewhere between this extreme case and a zero sediment budget, you might have an area where a site where sediment removal is always exceeding sediment accumulation. but not in an extreme way. And that may be gradually creating conflated deposits, where you're gradually getting a condensation of your archaeological remains. So you need to know, you need to have an eye to a sediment budget. I mean, at least you need to understand the concept that sediments can be removed and not just accumulate.
Like you, I've excavated in Britain, and the thing that struck me about those excavations was the planning of the trenches, the shape of the trenches, the placement of additional trenches was almost entirely based on the variation in stratigraphy across the site, and really thinking carefully about planning the dig based on what we knew about the stratigraphy, but what we were discovering about the stratigraphy. If you could perhaps comment on the Australian case, where it's been my experience, and it may have been yours, that digs don't really take into account the stratigraphy. People just go in and dig there's already a plan to dig a 1 by 1 or a 2 by 2, and I think the planning of a dig for the most part isn't really based on what the stratigraphy of the site is.
I think excavation has always got to be a dialogue with the site. You may have limited capacity in terms of the area you can excavate, so you may ultimately have to say, well, okay, I'm going to put a 1 metre square in the middle of the site, but you need to have you need to be asking what is happening in other parts of the site, and you need if you do have the capacity to do a large dig, you need to be probing those areas. I really want to know what's happening at the front of the site, what's happening in the middle of the site, what's happening at the rear of the site. They will differ in terms of their sediment characteristics, but they'll also differ in terms of how the site is used. I mean, characteristically, you might find the discard areas against the rear wall or against rockfall embedded in the floor of the deposit. So if you want to find grindstones or your larger stone artefacts, you've got to look for these secondary discard areas. The sleeping areas of the site with all the small sleeping files will be at the rear. The flaking areas might be towards the drip line. There's a lot of, where you place your trench makes a lot of difference as to what you're going to find. If you do have the luxury of digging more than 1 square metre, it's a process of, an iterative process of asking questions about the site and dissecting it in a certain sort of way. I don't think enough people are alert to the possibility that if you dig quite a small pit, excavation pit, you could actually come down inside an entirely intrusive feature. You may end up with something that bears no relationship to the rest of the site at all. And that's been done, actually.